Hello and welcome to this lecture on advanced electric drives. In the last lecture, we were discussing about the Swiss reluctance motor drive, how to control this motor, and we have seen that in a Swiss reluctance motor, the torque is produced by the variation of inductance. T is equal to half I square L dL by d theta. So, this is the principle of torque production. The torque is produced by this expression, that is dl by d theta into I square. Half of this is the expression for the torque, and hence the torque will be produced only when there is a position dependent inductance, and the inductance should be a function of time. So, if we see the cross sectional view of a Swiss reluctance motor or SRM, we can take a motor and take a cross section of that and see that both the stator and the rotor are salient in nature. So, we see here we have the stator core in this case, which is laminated. It is a laminated core. The rotor core is also laminated. We have the rotor here, and the stator is having saliency. These are the stator poles or tooth here, and we have the slots in this case in the stator. In the rotor also we have the rotor tooth. This is the rotor tooth, and we have the rotor slots also. So, the stator and the rotor both are slotted, and the stator carry windings, concentric windings, and this motor becomes a lightweight motor because the rotor does not have any winding. Rotor is only having slotted structure, lamination which are slotted without any winding, and hence the rotor inertia becomes very low, and the speed response of the rotor can be fast. So, if we analyze the inductance variation, we see that as the rotor moves, we have the rotor here and we have the stator in this case. The stator carries concentric winding. These are the windings of the stator. This is, for example, a particular phase, let us say phase A. We have the stator phase A, and the rotor pole or the rotor tooth is coming under the stator pole. Now, under this situation, if we see the inductance of the stator winding, this is the stator winding, this inductance will be gradually rising linearly, because as the rotor pole moves under the stator pole, the air gap in this case will be gradually reducing, and hence the inductance will be increasing. So, the inductance of this winding of phase A is a function of the position, that is theta, and after some time the rotor pole will be fully under the stator pole, and hence the inductance will remain constant. This is a constant inductance, that is L max. It started with L mean, changes linearly, and then remains constant when the rotor pole comes fully under the stator pole. Thereafter, the rotor pole goes away from the stator pole, the inductance reduces. This region is basically the region for which dl by d theta is negative. So, we can plot this dl by d theta for the rising condition from L minimum to L maximum. Dl by d theta is positive, and when the inductance remains constant, dl by d theta is 0, and when the inductance decreases, dl by d theta is negative. So, since we have the variation of inductance with position, we have a finite dl by d theta. It could be positive or it could be negative. Again, the expression for the torque, if you see, it is half I square dl by d theta, and hence for positive torque, I square is always positive irrespective of the fact that I is positive or negative. So, if we want positive torque, I should be concentrated during the positive dl by d theta. It means the phase current here, if this is the phase and if if this carries a current that is I, this I should be predominantly in the positive dl by d theta, not in the negative dl by d theta, because if the current exists during the negative dl by d theta, torque will be negative. I square is always positive. So, if you want positive torque, I square should only exist during positive dl by d theta, and that is the principle of torque production in a Swiss reluctance motor. The current in the winding has to be so switched, optimally switched in such a way the current only exists during the positive dl by d theta, and if we can ensure that the torque production is maximized, and we can have a motor with good torque per ampere. So, if we plot dl by d theta, we see that it is alternately becoming positive, then 0, then for this region from 42 degrees to 60 degree, again we have minimum inductance region, then we have the further rise, the next pole is coming under the stator. So, this is a periodic waveform, and dl by d theta is also periodic with theta is the rotor angle. Now, how do we control? We can control the current in such a way the current only exists during positive dl by d theta, and that is achieved by switching a voltage onto the winding. So, if we switch the voltage VDC onto the windings, we have power switches by means of which we can switch this voltage onto this winding, we will have a current that is I. So, we can write down this equation V is equal to Ri plus N d phi by dt is equal to VDC, that is the DC voltage. In fact, we can have alternative topology also for injecting this current. We can have a winding like this. This is a phase winding, and we can switch the voltage in the following fashion. We can have a transistor here is the electronic switch, and with this electronic switch we can switch the current onto the winding. This is one phase of the Swiss reluctance motor. So, we can switch the current onto this winding, and this is I, and this is VDC, and we will have a power supply with VDC like this. We have VDC and also another VDC here. In fact, we have a battery having a voltage of 2 VDC having a center tap, and here what we do, we connect a diode and the diode is D, and the switch, the transistor is S. So, when we switch the transistor S, the voltage across the winding is VDC. So, if we have this is A and this is the B terminal, we can say that this is the voltage that is applied here, that is VAB in this case is positive. So, we say that V is equal to VAB, the applied voltage is VAB, that is plus VDC when S is on and D is off. So, naturally when S is on, the diode is reverse biased and hence the diode is off. So, the voltage across AB, that the applied voltage is VDC. Now, when we switch up this switch S, the current through this winding is flowing from A to B, and that will be equal to, when we switch off this S, this current through the winding will be maintained because it is an inductive current. So, the current through the winding has to be continuous or has to be maintained when the switch is off. So, the current will try to find out an alternative path, and the alternative path will be through the diode. So, it will flow through the diode. Earlier it was flowing through the transistor, now it will be flowing through the diode, and the diode turns on and S turns off, and as a result we can see that VAB will be in this case minus VDC, that is equal to minus VDC when S is off and D is on. So, in fact, when we switch on S, I increases, and when we switch on or switch off S, I will decrease. We are applying minus VDC to this particular winding, and the current will fall quite quickly. So, we can apply both plus VDC and minus VDC through the winding to control the current. So, by controlling this current, we can control the torque, because we know that the torque is proportional to I square. It is in fact half dl by d theta into I square. So, if we can control I, we can control the torque. Now, how to control I in a proper way? Because I has to exist only during positive dl by d theta. So, in fact, if we see the diagram here, that will be clear. What we have in this case is the following. We have the inductance variation, this is L. L is sometimes minimum, sometimes L is rising, it reaches L maximum, then this decreases, becomes again minimum, again rises, reaches a maximum value, and again falls down, and this repeats. The x axis is theta, the rotor position. Now, if we plot dl by d theta, this is L, the dl by d theta in the same graph will look like this. During this time, dl by d theta is 0, because L is constant. In fact, this is L minimum, this is L minimum, and this peak is L maximum. So, if we plot dl by d theta, we can say that here it is 0, then dl by d theta is positive, then L is again constant at L maximum, dl by d theta is again 0, and then L decreases to again L minimum, this is again L minimum at this point. So, dl by d theta is negative here, and here is again 0, and this is periodic, this continues like this. So, our objective is to switch the current in such a way it only exists during positive dl by d theta. So, we switch the current in the following fashion. Now, we have already seen that we have the equation, the voltage equation will look like this: V is equal to Ri plus N d phi by dt, the rate of change of flux linkage, and that is equal to the applied voltage, which is plus VDC. And we ignore the resistance drop here. The resistance drop is Ri, so we can ignore this resistance drop Ri in this case with respect to the induced EMF N d phi by dt. So, if we say that Ri is neglected, we can say that V is equal to N d phi by dt, and that is equal to applied voltage, and the flux can be found out by simple integration. Omega is the speed. If we divide by speed and multiply by speed, we get the expression integration of VDC by N omega d theta, and that is simply VDC by N omega into theta. So, in fact, what we observe here if the speed is constant, the flux is linearly proportional to theta when we apply VDC. So, theta will increase and the flux will also increase linearly with theta as per this equation. VDC is applied, which is constant voltage. We are assuming a steady speed, that is omega is constant. N is the number of turns of the phase of the stator, that is also constant. So, if we apply a voltage, now how to apply the voltage? The voltage is applied in the following fashion. The voltage is applied in such a way that the current rises and remains for dl by d theta positive. So, we apply the voltage here, this is V. In this case, we turn on this switch S and the voltage becomes VDC. So, if the voltage is VDC, the flux will rise linearly. So, what is the flux? The flux will rise like this. So, this is the flux waveform phi, and here we have the voltage, that is V. And then if we have obtained flux, how do we obtain the current? Ultimately, the current is something that decides the torque. Current can be obtained from the flux, and we know that inductance is flux linkage per ampere. N phi by I is inductance, and we can say that current is nothing but N phi by L, and we know what is N phi. So, N phi, we can substitute phi here. So, if you substitute phi here, I is given as VDC into theta divided by omega L. This is an important equation. This equation is extremely important because this gives the value of current when you apply a voltage, that is VDC. I is equal to VDC into theta divided by omega L. So, what is omega? Omega is the speed of the rotor. What is L? L is the inductance, which is not constant. Inductance can be a very small value, it can be a large value. It increases linearly from L minimum to L maximum. Speed can also be a variable. So, I is not only a function of theta, but also a function of the speed and the inductance, also the applied voltage. So, under this situation, we can say that I will proportional to VDC. So, it is basically proportional to VDC, but it increases with theta also. So, if we plot I in this case, I will start from 0, and here the inductance is L minimum. So, I will rise almost linearly, and at this instant inductance is increasing. Now, this is the initial rate of rise of I. So, what is this rate of rise? The initial rate of rise is given by di by dt is equal to VDC by L minimum. We have applied a voltage, that is VDC, and at that instant when we are applying the voltage, the inductance is a minimum value. So, when the inductance is minimum, current can change quickly. If the inductance is large, current will not change that quickly. Inductance opposes the change of current. So, when the inductance is minimum, we have applied a voltage, current can change quickly and reach a high value. So, the current rises and reach a high value here, and then the inductance is trying to increase. Now, when the inductance increases, current growth will be arrested because inductance will oppose the change of current, and thereafter the current rise will be still there, but it will be arrested. This won't be rising with that particular slope, it will be reduced. And then we have to make the current 0, because we don't want the current to stay long enough for the negative dl by d theta. This is basically the positive dl by d theta, and if the current is allowed to flow, it can also flow during the negative dl by d theta. So we apply a negative voltage, that is minus VDC. So what we do here, the voltage is reversed and we apply a negative voltage in this case. And when we apply a negative voltage here, the flux is going to fall. The flux will be falling like this, because flux is proportional to VDC. So if VDC is positive, the flux will increase in a positive direction. If VDC is negative, flux will reduce and it will become 0 after some time. And then the current will be reduced because we have applied a negative voltage. So the current will also become 0 after some time, but initially the inductance is quite large. Inductance here is quite large, it is increasing. So the current rate will be low here, it will reduce but with a low rate, and then it remains constant. So it will somewhat decrease and become equal to 0. So this is, current has to be so adjusted that it only stays during dl by d theta, which is positive. So this is how the current pulse looks like. This is the phase current. The current is only present during dl by d theta positive. Now when the inductance rate will be negative, the current should have died down to 0, and if we can ensure that the torque is optimized, the torque remains positive. So this is done by proper switching of the current, so that it is only present during positive dl by d theta. Now if we see this current expression that we have already derived is the following: I is equal to VDC theta by omega L. Now this is the current. What about the torque? Torque is equal to half I square dl by d theta, and dl by d theta is a constant quantity, that is positive, and we can replace this dl by d theta by some arbitrary constant. So we can say that is equal to k into I square. Half is a constant, dl by d theta is a constant, so t is equal to k into I square, and that is equal to VDC theta by omega L into the same thing VDC theta by omega L into k. Now we can also find out the mechanical power. This is the torque, and the power is equal to torque into speed. So we can calculate the power by the following equation: P is equal to T into omega, and that is equal to k VDC theta by omega L into VDC theta by L. So this is the mechanical power output. So this is same as P out. So this is what we have here. Now when we operate a Swiss reluctance motor, it is operated in various modes. When the speed is very low, current will rise quickly, because we have already seen the expression for the current. And we see that is omega is small, close to 0, I will rise very quickly, and if omega is medium, the rate of rise of current will not be that fast. If omega is large, the rate of rise will be still low. So I depends upon the speed. So we can plot I for various speed. Say for example, if speed is very low. So if the speed is very low, we can plot I will rise like this. This is, let us say, A, waveform A. The current rises very quickly. What you are plotting here is I, and this is against maybe theta here. So, this rises very quickly, and if the speed is medium, it rises, but not as fast as A, but it rises like this, stays, and then falls down. This is B, let us say. And if the speed is low or speed is high, it will change like this. So, we have three different situations. This is for A is for low speed, B is for medium speed, and C is for high speed. Because the current is inversely proportional to speed, and hence at low speed the current will build up very quickly. Now, how do you control the current? The current is controlled what is called in a chop mode. So, at low speed we employ chop mode. So, this is basically called the chop mode. By chop mode we mean we apply plus VDC and minus VDC in such a way current is limited to a band. So, we want the current to be constant during positive dl by d theta. So, we switch VDC and minus VDC in such a way the current is limited within two bands. The bands will be defined around the reference value of current. So, this is the reference current, let us say I star. So, we can define a upper band and we can define a lower band, and we can switch the voltage in such a way that the current stays within the band. So, this is how the current is controlled, and for the rate of rise to be positive we apply plus VDC, and when we apply minus VDC the voltage is negative and the current decreases. So, we alternately switch on plus VDC and minus VDC so that the current stays within the band, and this is called chop mode, because we are chopping the applied voltage high and low, high and low. And if you see the input voltage waveform VDC, it looks like this. Initially we apply a voltage that is plus VDC, and then the current rises to certain value, and then we apply minus VDC, it decreases, then we again apply plus VDC, then minus VDC, then again plus VDC, and again minus VDC. So, the current will rise very fast and also fall very fast, because the speed is low. So, it can rise and fall very fast. So, rises and falls, again rises and falls, rises and falls. So, this voltage is plus VDC and this voltage is minus VDC. This could be against theta. So, this is how the current changes, and since we are changing the voltage, this is called a chop mode. So, we have various modes of operation. Modes of operation of switch reluctance motor. The first mode is called the chop mode. So, this is basically at low speed. I is maintained constant, maintained within two bands by switching the input voltage alternately between plus VDC and minus VDC. So, this is achieved through a power converter. So, we can have a power converter by means of which we can apply plus VDC to make the current rise and minus VDC to make the current come back to again the original value. So, it is maintained within a band, and this is for the speed omega less than omega b. Omega b is the base speed. So, up to the base speed we can go for chop mode. Now, beyond base speed, what we do here is this, that the rate of rise is not very fast. So, the current does not rise quickly. So, what we do in this case, if we see this expression that the torque has to be maintained constant. So, we can keep the current constant up to the base speed. So, this I is kept constant by controlling this current within two bands, and hence below base speed we employ the chop mode, and that is also called constant current mode, constant torque mode. So, we say this also to be, this is also known as constant torque mode. Now, what happens after the base speed? After the base speed we have to maintain the current, and the current does not increase so quickly because the speed has become large. So, what we do, we do not keep the current constant, we try to keep the power constant. So, in fact, after the base speed we go for constant power mode, and that is controlled by controlling theta. So, we call that to be the advanced angle control. So, we do that by I is controlled, I is not kept constant, T is also not kept constant, however, T w or T omega is kept constant. What is T omega? Let us go back and see the expression for T omega. T omega is given by this expression. This is T omega. In this case, we do not keep T constant, but we keep T into omega constant, and speed is increasing. Gradually the speed is increasing. So, VDC is constant, inductance is almost, let us say, constant here. Inductance may be variable, but our objective is to keep the power constant. So, for this we adjust this theta with omega, and that is called advanced angle control. So, we can adjust this theta to control the power, and power is kept constant to change theta. So, in this case we can, P is given as T into omega, and that is equal to, we have the expression for this power, K VDC into theta by omega into L into VDC theta by L. So, in fact, we can say this is theta naught here, and theta naught here is called the advance angle. So, with the increase of speed we increase theta naught so that the power remains constant, and that is called the advanced angle control. And this goes up to some speed, and once you increase this theta naught reaches its maximum value. So at theta naught equal to theta naught max, you cannot further increase theta naught. So when theta naught reaches theta naught max, theta naught is kept constant. So we have the expression for the power in this case, P is equal to K VDC square theta naught square by omega L square. In this case, theta naught is kept constant, and hence what is constant is not P, this is T into omega. So T omega square is equal to K VDC square into theta naught square by L square, that is kept constant. So we have three different modes: constant torque mode, where it is operated under the chop mode; constant power mode, where T omega is kept constant; and we have the third mode, which is called T omega square constant mode, where T into omega square is kept constant. Now we can explain the various modes of operation. We have already seen that we have a constant torque mode, a constant power mode, and a constant T omega square mode. Now when we talk about this advanced angle control that we are just discussing, what is this advanced angle theta? So this theta is called the advanced angle, and the advanced angle is controlled in such a way that the power remains constant. Now this will be clear if we see this inductance variation with theta. Now this is the variation of inductance with theta. The inductance rises in this case from L minimum to L maximum, then from L maximum to again L minimum, and again it remains at L minimum, and this continues. When the speed is very low, the current builds up quickly. So we have to operate that in the chop mode. So the chop mode means current has to be controlled in such a way it remains within a band. So this is how the current is controlled. And then before the falling of the inductance, the current is brought down to 0. So it is only confined during the positive dl by d theta. Now when the speed becomes large beyond the base speed, this mode is not preferable. So but still we have to maintain the power. Current has to build up. So what we do, instead of switching at this age, we switch at a little earlier. So this is L minimum, this value is L minimum, this is L maximum. So we switch the voltage, the positive voltage, little ahead. That angle is called the advance angle, angle by which the voltage application is advanced is called the advance angle. So instead of applying the voltage here, what we do in this case, we apply the voltage little earlier, and when we apply the voltage little earlier, current will have time to rise. So in this case here, when the voltage is applied, the inductance is L minimum, current can rise quickly. So this will rise, and then this will go into a region where there is a plateau, and if you apply a negative voltage, current can again come down. And with the increase of speed, we have already seen that the current is given by VDC into theta by omega L. So I is equal to VDC into theta by omega L, and here we can say that it is approximately theta naught, because after the inductance rises, there is no scope for the current to build. Current can only build up during L minimum, because this L minimum is a low value of inductance during which the current builds up, and when the inductance rises, the current build up is arrested. So, we can control this advance angle. So, this theta naught is increased in such a way that the current rises quickly during this L minimum, and with the increase of speed, when the speed increases, we increase theta naught in such a way that current is still maintained. So, what we can do here is that we can have another situation. This is our advance angle here, theta naught. We can apply the voltage little earlier to this also. So, we can apply it earlier to this, and the current can rise still quickly here, and then we can apply a negative voltage for the current to die down to 0, and then we can still increase this, but how far? We cannot increase infinitely. So, up to this region. So, this advance angle has a limitation, because this inductance variation is periodic. So, if you go on increasing the advance angle, we may hit again the negative dl by d theta region. This is the region in which dl by d theta is negative. So, we should avoid the current existence during this region. So, this is our maximum advance angle. So, we can say that the advance angle has a limit, and this advance angle is theta naught maximum. So, after theta naught become theta naught maximum, we cannot increase the advance angle. So, we have to go for t omega square constant. Now, we can divide this various operating region into 3 regions, as we have already discussed. The first one is the constant torque region. Let us see. What we are plotting here is as follows. We are plotting here the torque versus speed. The first region up to the base speed, this is our base speed omega b, is called the chop mode. This is also called the constant torque mode. Then we go for advance angle control, where theta naught is increased, and we enter into constant power mode. And this mode is called advance angle control or theta naught control, and this is known as constant power mode. Here we reach the maximum theta naught. At this instant, theta naught is maximum. We cannot go beyond the maximum theta naught. So, we enter into t omega square constant. So, t omega square is kept constant after theta naught reaches theta naught maximum. So, constant power is t omega is constant, and this region is called t omega square constant, and here we have to stop it at a speed called the critical speed. Beyond this speed, the machine will not run, because the bearings etc. will begin to fail. This is limited by the mechanical constraint of the machine. So, the machine has been designed for a maximum mechanical speed. Beyond this, the machine will not operate. So, this is the critical speed. So, we have 3 different modes here: the constant torque mode, the constant power mode, and t omega square is constant mode. Now, let us now see a closed loop speed control block diagram of a Swiss reluctance motor. closed loop speed control of the Swiss reluctance motor drive. Now, here we will start with the reference speed. Our objective is to have a variable speed operation. We take a reference speed and we control the machine with a closed loop speed feedback to have a variable speed operation. So, we start with a reference speed here. That is omega star, and we compare this with the actual speed of the motor. Then we feed this to a PI controller, a PI regulator. We have a speed error, that is E of omega. The PI regulator will give us something similar to the torque. We can have a limiter as well. A limiter, only we need the positive value here. So, this is the torque, and then we have a square root block in this case, because T is equal to K I square approximately. So, we can have a square root block here and we get the reference phase current I star. This phase current has to be injected into the motor windings for every phase, and then we have a comparator here. The reference is compared with the actual current, and the actual current is I, and this is fed to a controller block, controller. We can say it is basically the current controller, and then we have the converter, and then we have the motor. Swiss reluctance motor. And the output here is the speed. The speed is fed back for the closed loop control. So, we can have the speed feedback from this. Speed is fed back here, and this I is obtained from the motor. We can have this current sensor to sense the phase current. So, this phase current is fed back for control. Now, we also need the position. The position information is obtained by integrating the speed. We can have a position encoder, or we can integrate the speed to find out the position, because theta information is quite important. So, the converter has to be switched in accordance with theta. It is basically position dependent switching. The phase has to be applied with voltage with synchronism with the rotor position, and hence we need the information about theta, and theta can be obtained by integration of the rotor speed or by a speed encoder, also by absolute shaft encoder. So, this is theta in this case, and we also require information about the speed here, because we have various modes of operation. So, we have this omega information here, and for the negative torque we need to adjust the position. So, this error is fed to a sign block. This sign block will give either a positive or a negative sign, and depending upon that we can have a positive torque or a negative torque. So, this also goes to the controller. So, this is the closed loop block diagram of a Swiss reluctance motor drive, in which we can go for a variable speed operation. Below the base speed we can have chop mode. We have the speed information which is available here, and the controller will be in the chop mode for the speed below the base speed. Above the base speed, we can go for advanced angle control or theta naught control, and above theta naught maximum we go for t omega square equal to constant till the maximum speed is reached. So this gives a complete range of speed operation from 0 to the maximum speed. And when we need negative torque for the speed reversal, the speed error, this E omega, is usually negative. Now we understand that T usually is equal to half I square dl by d theta. So if we want to have positive torque, we have to switch the current in positive dl by d theta. But if you want negative torque, the torque can be reversed not by reversing I, but by making or switching I when dl by d theta is negative. So T is positive if I exists during dl by d theta positive. T is negative if I exist during dl by d theta that is negative. So we can have the proper switching so that we can make the torque positive by switching the current in positive dl by d theta, or if you want the torque to be negative for deceleration or for braking or for speed reversal, we need to have negative torque, and that can be ensured by switching the current during negative dl by d theta. Now let us try to see the various topologies used for converters. We understand that converter is very important for switch reluctance motor drive. Now unless we have a converter, we cannot switch the current. Now we will see a few examples of converter used in SRM drive. So the power converter topologies will be as follows. A simple topology we have already discussed. We have two voltage sources and we have a transistor like this, we have a diode, this is VDC plus minus, and we have the phase inductance. If this phase, this terminal is A, this terminal is B. So if we want positive voltage, we switch on S. If we want negative voltage, S is switched off and we switch on D. We have a little different criteria. In this case, we need both two supplies, VDC here and VDC here. So a little variation can be seen if we can manage this same thing by a single supply. So we can have a single supply here, VDC, and then we have a positive transistor, and we have a transistor here, and we have two diodes here, one diode here and the other diode here. Now here this is A and this is B. So we have a single voltage source, that is VDC. So if we want positive voltage, we switch on transistor S1 and S2. So the voltage VAB will be plus VDC. If you want to reverse that particular voltage, what we do? We switch off S1 and S2. If we switch off S1 and S2, the diodes will be conducting. This is the direction of the current which flows through the winding, and if we switch off S1 and S2, this current has to be maintained through the diodes. This is diode D1 and D2, and hence the voltage applied across AB will now be negative. So this is the topology which is more popular. This is for phase A, and similarly we can extend this for phase B and C, and this is one of the converters that is used for switch reluctance motor. In the next lecture, we will be discussing about few more converter topology which are used for Swiss reluctance motor drive, and also we will have an introduction to the stepper motor. The stepper motors are used for position control. They are also based on the principle of reluctance variation that we will see in the next lecture.